What's up, guys? Welcome back to another episode of Stonks Maxim. Today, gonna go over some practice problems to prepare for my computer architecture exam. So I think I have 2 more days. I guess one more day really of full studying, and some of the key concepts we covered: speed up, so using Amdahl's law, pipelining, instruction set architecture, specifically MIPS 32, and performance as well. Performance, and I would say reliability. So those are sort of the few different concepts we covered. I want to say, let's see. We're gonna have to do a lot of sort of GPT prompting to maybe check some of my assumptions. Practice set 2. Okay, let's do practice set 1. All right. Okay, so this is heading 2 to question 2. So this is reliability. Probably spelled that wrong in the YouTube heading. Okay. So failure in time is equal to 1 divided by the mean time till failure. I think from my notes, I do have, we're allowed 1 cheat sheet for, let's see. Yeah, we are allowed 1 cheat sheet for the test, and I'm gonna say, so failure in time is usually reported as failure per billion hours of operations. Okay, so suppose we have a single processor with a failure in time of 150. So this means that we have, this is 150 failures per billion hours. Okay. 50 errors every 1 billion hours. So what is the mean time till failure for this processor in hours? Which is equal to, so this will be 1 over 150 billion hours. Right? Is that all there is to it? mean time till failure. So if you take e is equal to 1, let's see, not e, but let's do 1 divided by 150, so 0.006. Zero point zero zero, I think this is a basis point 66. Okay. Text billion hours. Yeah, this like thing is annoying me right now. It's so tight. There we go. Okay, my hand feels free. Okay, it's equal to 0.006 billion hours. So this is, I think if we were to multiply by 3, it'll be 6.6 million hours. Right? .6 million hours. Which equals 6,000 hours. Okay, I'm gonna put that there for now. Let's see if that's right. Assume that a 100 processor system is using the processor above. Also assume that it takes 30 days to get the system running. Again, once the system crashes, what is the availability? Okay, so availability is mean time till failure. So we got this, 6.6 million hours, divided by mean time between failures, plus the mean time to repair. So mean time to repair, yeah, there's no way. This is 6.6 million hours. What if we took 150 divided by a billion, right? 150 divided by 1, 2, 3, 1, 2, 3, 1, 2, 3. Yeah. Okay, and then we multiply that by one divided by that. So 1 divided by answer 6.6 million hours. Because it's 30 times 24, 720 plus 6.6. I mean, it's still kind of like 6.6. Pretty much 1, if that's the case. So if we have 100 processors, does that mean that our mean time till failure scales about 100 too? I don't think so. So failability is equal to time to failure divided by plus mean time to repair, which is equal practically 6.6 million divided by 6.6 million, which is, say, is approximately oops, approximately 1. Okay. Yeah, I think that's probably good. So that's really good. That means it takes a really long time to actually fail, and then the system is pretty much readily available. Now, I do kind of want to see if this is right. What is this? So this is kind of a misnomer. It should be 10 to the 9th. Yeah, so I think I got this right. Very close to being right. Okay, I guess this is pretty good actually, because I think when this question asks specifically in hours, maybe that's when you can do the 10 to the 9th. But as long as I sort of remember the form, which is equal to, it's 6.6 million. Right, and then we have 6.6 million plus, and then plus what? So we have 24 times 30. It's equal to 720. If I'm not mistaken, yep. Yeah, which is just pretty much exactly. Okay, so assume that okay, this one I'm gonna need to really write down because I don't remember all of these. So MIPS 32. So SLT, what does this do? What does the SLT instruction do? Oh, I see. Okay. Destination. R1, R2. Compare R1 and R2. So I think R1 is less than R2. So if R1 is less than R2, then sets, so the destination register to 0, so else f to 1, else 0. Okay, so we need a load double word, and then what we're doing here is we're taking the original memory address, I think 2000, 2008, 2016. We don't need to offset, we'll just get the value. So A is equal to 4. B is equal to 8. C is equal to 10. Okay, so SLT, what we'll do then is we'll take, we'll call this R5 to store a value 0 or 1. And what we want is we want to compare if A is okay, so if B is less than A, so we compare B is less than A, and in this case that is not, so B, we'll call this equal to call it B equal to 0. I think that's probably going to be the best. Yeah, so we could just say is R5 equal to 0. Actually, yeah, if it's equal to 0, then we just go to skip. We don't actually run this. Set R1, R5 to 0. Oh, to 1. So skip if B is less than A is true. All right, and then what we'll do here is if A is greater than or equal to B, then we don't actually jump branch. And what we'll do here is we will add, so A and B together, put in R3, but then we need to store, we need to make this negative here. So I feel like all we need to do is just flip the bit, but I don't remember the exact. How do I flip the sign of a 64-bit in MIPS 32? Hmm. No, we don't even need C, really. Okay. One R2, so if just 0 A's, so that means A must be greater than or equal to B. It's not. Okay, so skip. Hmm. I feel like the answer that we got here is wrong on the. So what does D sub do? Oh, you could just take 0 minus. Is DADD a MIPS 32 or MIPS 64 instruction? Oh, I see. sub, so we have R3. So we just take 0 and then we just subtract R3. So 0 minus R3, then that should just flip our sign to negative, right? What if we want to go from negative to positive? Same thing. I think we just do 0 minus R3, and that'll give us the flip. Okay, so I think this is wrong here. What we need to do is get the 0 register, and then we just access it like so. So 2008. I wonder if it's wrong to do the way I did. Is wrong to load a value memory address using the following syntax. So R1 oh, I would have to do load immediate, I feel like. This also wrong. So load R2 2000. Okay, the base and then offset, right. So we needed the base offset style, okay. So this is definitely not right. Okay, so if A is less than B, then we'll set R5 to 1. In this case, they do if B is first register is less than the second register otherwise. So if B is less than C, so if B is less than A, which is the exact same, so if B is less than A, then this will be 1. B is greater than A, Oh, I see, okay. So B is less than A. So don't skip if B, right. And if it is, then we do skip. So we have 2016, and this will be 0. Okay. So this will be negative A plus B. Then we store back into C. All right. So what does it mean by, what does it mean when instructions are executed dynamically? Okay, so I guess it depends on what the actual, So what is for sure, right? We know this is for sure. This is during compile time, I think. So set less than. Do we know this for sure? Probably not, right? I'd imagine that these are probably the instructions after we've loaded in everything that will run. Differently depending on, it could even be this. Okay, I don't know actually. So given this assembly, I guess dynamically just means that there's just how many instructions are executed, right? In this case, we have just flow through the code to see what happens. I think that's really all we need to do. Let me see how's the stream going. Hey, exam maxing. Okay, so I think from this problem we were given that, okay, so there will be 4 instructions because these two are guaranteed to run. We always load in A, we always load in B. But in this case, I think, okay, also this. So at least 3 are guaranteed. But in this case, is B less than A? No, it's not. It's actually greater than A. So B is equal to 8, A is equal to 4. So we set this R5 equal to 0. Then we compare 0 with 0, and we just skip. So we only run 4 instructions because B is greater than A. So the instructions will jump past the executed B2 memory data references, just the 2 LD instructions. So in this case, we have 1, 2, 3, 4, 5, 6, 7. So we have 7, not 8. So 7 times 56. Okay. Oh, sorry. 8 times 4. 7 times 4, which is 28, right? 7 instructions, each instruction is 4 bytes. I'm confused then. How is each instruction, right? So in MIPS 32 is 64. Is each instruction 4 bytes? Coding, so, okay. Is this, do instructions in MIPS 32 also have the same length? Okay, so MIPS 32 and MIPS 64 have pretty compatible architectures then, because the instructions are just 32 bits, but I guess the actual operations are slightly different. Alright. 4 bytes each instruction, 32 bits long. Makes sense. The C is equal to negative A plus B section of the code. Okay. Okay, so if b is equal to 8, then what we'll do here is maybe, so b is equal to 8, load data, okay, here we go. 16 bits. Yeah, so this is definitely wrong. We don't even need a load C actually. So let's put R1 2000 and we'll offset from 0, right? So offset from 0, get load B. Okay, so set less than, so what does this do? This will compare the two, right? So we have the same idea. I think what we can do is set R3, call this so R2, and then R1. So if B is less than A, set to 1, else 0. Alright, so then we do b not equal, I guess we could do b equal. If R3 is equal to 0, then we'll go to else, and we'll have this here. If so R3 is equal to 0, then jump to else. Okay, so I think this is shift right logical. We do the shifting here of A, and let me see. Okay, so shift, and then we'll shift A 16 bits, and then we'll also flip this around so it's negative. So shift right logical, and then we'll do B sub. So we got R2, right? And then R2, 0, and R2. So this is how we get the negative A16. Okay. All right, so get that. It's good. So we just jump to the end, or we just shift left logical, and then what we'll do then is we can just change R2, I think, right? Yeah. And we don't need to actually do this. Yeah, what happens with integers overflow? Okay, end, just store what we'll do is we'll take 2016, and then we want to store R2, right? Okay. So how many instructions are executed dynamically? I guess, first of all, is this even right? Oh, we need to add a D in front of all of these. Okay. So D, SRL, shift left logical. Jump end. Okay. Right. 2016. Guess, yeah, maybe we gotta add this here, not just at the end, but after the instruction is done. Okay. So if that's the case, how many instructions are executed dynamically? All right, so let's see. What is A again? Oh, god damn. Whatever this number is. Okay. 0x000. 1, 2, 3, 4. Okay, just set that for now. FEDC. Okay, so with that, I think what we could just say is that B is bigger than A. So what we'll do is we'll else so we definitely run at least these. So B is greater than A. So we'll run 4, and then we'll jump to the else, and then what we'll do then is we'll run these two. So there's going to be 6. There will be 6 instructions executed. So what are they? So 4 before 4, so before branch instruction plus 1 branch instruction, right? And then 2 after else label. So 6 total. How many memory data references will be executed? So we have 1, 2, 3. So 3 total memory. So 2 loads, 1 store. Code size in bytes. We have load data. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I think what we could do here is just so code size is equal to, what we'll do is we'll take the instruction size times num instructions, which is equal to 4 times, I think we said it was 9. All right, I'm getting some errors here. Okay, 4 times 9, right? 1, 2, this is 4, 5. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's actually 10, which is equal to 40. Let's go. All right, value in hex. So this one actually might be kind of hard. So address 2016 after the code execution. Right, we've essentially replaced this value to A shifted right. Sorry, shifted to the left. So we look at the arrow here. Shifted to the left by 16 bits, so that's 4 bytes. So essentially we add 4 zeros here. Yeah, we could do that. So we'll get A here. I think this is 1, 2, 3, 4. So we push that. We get 1, 2, 3, 4, 0, 0, 0, 0, FEDC 0, 0, 0. Okay. The value in A gets shifted left. So insert 4 zeros from right to left. Okay. Insert 4 zeros starting from the right hand side. Okay. The value in A gets shifted to the left 4 times. So final value is 0x. I think it's 1, 2, 3, 4, 0, 0, 0, FEDC 0, 0, 0. Okay. I think this should be good then. 2, 3, 4, 0, 0, FEDC 0, 0, 0. Got it. All right, nice. Gonna use the bathroom real quick, actually. Let's see if we can speed through this one. So, availability. Assign 2 questions. Interesting. All right, practice 1. So if a company has 10,000 computers, let's just see this. Okay, so heading question 6. A company has 10,000 computers, each with a mean time to failure of 35 days, and it experiences catastrophic failure only if 1/3 of the computers fail. What is the mean time to failure for the system? Okay. Is this a trick question? Is it not just so it experiences catastrophic failure only if 1/3 of the computers fail? What is the mean time till failure for the system? Is it not 35 days? Enhancement to a computer that improves the mode of execution by a factor of 10. Okay, I'm gonna skip this one for now. It's not super clear. Question 7. An enhancement to a computer improves some mode of execution by a factor of 10. Enhanced used 50% of the time, measured as a percentage of the execution time when the enhanced mode is used. By a factor of 10, right? So Ohm's law, call this speed up, and law, old time over new time, which is equal to 1 over 1 minus f plus f over s, fraction divided by speed up. So if this is 100% we use our fast time. S over F. This is really, really big. Oh, wait, F over S. So it is F over S. Because F is the fraction in fast slash is parallelizable. S is equal to fraction. Speed improvement. .5 divided by 10. Enhanced mode is used 50% of the time, measured as a percentage of the execution time when the enhanced mode is used. Fraction of the original unenhanced execution time. So speed up we have obtained from fast mode. So we can't just do 1 minus 50% plus 50%. So that'd be 0.5 plus 0.5 divided by 10. So 10, that would just be 0.05. So 0.05 plus 0.55, that's about 2. Enhanced mode is used 50% of the time, measured as a percentage of the execution time when the enhanced. So how long is the enhanced mode used, right? So 50% divided by 50%. So how much time is the enhanced mode used? Alright, I don't know, this wording is weird. Like, I feel like this is 50% is equal to, call this enhanced mode use. So time when enhanced during enhanced mode. Enhanced mode. So I guess there's like a meta to it almost, sort of like a second layer. Yeah. I'm kind of curious. No clue how this is. So can you explain how this is correct? Okay, let's see. of enhanced mode. Okay. S T new is equal to T new is equal to F times fraction that is enhanced times the old divided by, so this is the enhanced part plus the unenhanceable part. Oh my god, this is pretty hard. So for T old in terms of T new, so enhanced time is equal to 5. Okay, yeah, so T new is equals T old. Divided by T old. Oh, is this simple algebra? Okay. So enhanced parts equal times our enhanced time. Just divided by T old. Yeah, I don't know. This doesn't really make too much sense. Yeah, maybe this one might be a good question for Piazza. Oh man, I have a feeling this this exam is gonna be pretty tough. Ah, shoot. So there are office hours though, which is interesting. There are office hours before class. All right. How can terminal old execution time ratio. Time is equal to 1 minus f. Oh, okay. Times all execution times 5.5 new time. Okay, there's a question on, let me see, question practice 2, 5B. Oh man. Alright, yeah, I'm gonna, okay. Yeah, I think I'm gonna probably end this one here. Let me see. Yeah, this one was a bit confusing. I have to see. So failure time of each machine. Failure in time. Failures in time. Failure rates. As a machine solo, 10,000 times 1 divided by 34 is equal to 35. For every 0.003. Okay, so you just sort of just add them. Interesting. All right. I'm gonna create deck. Reliability. So company has each computer has a failure in time of failures. Call this a failure rate of forgot to do math on this. Command EE, Command MM. Okay. Frac 1 divided by 35. So the system is the combination all 10,000 computers. So it'll fail usually 1 out of every 35 days. Yeah. Fail 1 time every 35 days. It's the combination of all 10,000 computers. The failure in time is the system is 10,000 times failure rates. So we have 10,000 times 1 divided by 35. Failure rates of the system is so is 10,000 times the failure rate of one computer. Okay. Which is equal to, I think, 10,000 divided by 35. I don't know what that is. It's a divider. And 285.71. And 285 computers fail every 35 days. Yeah, I don't think this one's right, actually. It's a combination of all 10,000 computers. So what? Burp. Maybe that's like a percent, right? 27% chance, or like a 5% chance of failing. 10,000. The mean time till failure of the system is divided by 10,000. The failure rate of system flip that around. Yeah, I think. The mean time till failure is $35.7. This is a 285% chance. It's twice the amount of chance of failing every day. So one computer fails every 0.035 days. right? 1 divided by 0.0035. Okay. Farm will crash if 1,334 machines crash. So compute times MTTF, which is equal to around 11.67 days. One computer system is yeah, to double check. Alright, I think with that, I will catch you guys tomorrow. Peace.